Hello everyone, it's Mr. Homer here. I hope you're all well and happy and content and making the best of this strange time, which will come to an end at some point, and we'll all get back together again, or at least some of us will, and maybe in a smaller class size or what have you. But in the meantime, here's a little video of me going through these questions which we set you, and I'll just point out some common mistakes that I've seen when looking at your work. Thank you for submitting. Those who haven't yet, you still can, and even if you don't, use this video to after you've had a go at the questions and just go through it. The mark scheme's up there as well, but me going through it might provide for a little bit more entertainment, perhaps. Speaking of which, if you watch this all the way through from beginning to end in one go, I think it'll be damaging to your health. You'll fall into some kind of coma, I think. So I wouldn't suggest that. Stop it after each question and go through the question yourself just to check that you've got it all and you're all good, and rewind and go back or something. Don't attempt to do this all at once, because I'm aware that it can be a little, you're probably already asleep. So if you are, I hope you benefit from the nap, but no, do stop it and take a break and come back. Anyway, let's go through this with minimal waffle now that I've waffled. Question 1 was a air track with a glider, and this mass, when let go, pulls the glider. Now, of course, the force is constant, and with constant force we get constant acceleration. So, and that would happen until the mass hits the floor, at which point there's no force anymore on the glider and it won't accelerate. So the two boxes to tick are that the acceleration would decrease to 0 because the mass holder hit the ground before the card passed through the second gate. So before the results are complete, the accelerating force drops to 0 when the mass holder hits the ground. So the acceleration would decrease to 0, you see. And the second box to tick is that the resultant force on it would decrease to 0, because for the same reason, right? So got those two? Good. Then we have how could the student ensure that the mass holder should not hit the ground before the card passes through the second light gate. Where's the light gates? There and there. So what you do is you would shorten the string, wouldn't you? Obviously. Or a lot of you said move the second light gate towards the first. It would close that gap and it would ensure that it gets there before the mass holder hits the ground. Super duper. Then on to the next one. We've got this results table, and she's calculated the mean acceleration. The two mistakes are why write this to 6 sig figs? That's ridiculous. So obviously just give it 2 sig figs. You should say what it is, 1.3. The 6 means the 2 rounds up to 3, right? 1.3. And the second grave error is that I've called it the 5th result. Look, this bottom one here. 7.2, if you look at the pattern in these results, they're all pretty close, aren't they? To within 0.1 meters per second squared, apart from this one. Boom, anomalous. Discard that, calculate the mean, it should be 6.4. Right, moving on, we have this part D. It says right conclusion. Well, simple conclusion actually, which you can see from here is, look, as the resultant force doubles, so the acceleration doubles, more or less, to within 0.1 of a meters per second squared. That's 1.3, right? So look, that's practically a doubling. 1.3 to 2.6, that's a doubling. Then you can see, look, compare those two. Practically a doubling, and this is, yeah, 2.6 doubled is 5.2 or 5.1 within one unit of the last unit. It's a doubling. So this is directly proportional, isn't it, everyone? So yeah, I guess you got that. Lots of you said that. You are allowed to say that the resultant force increases as the acceleration increases, but that's fine. But directly proportional is a better answer because it's more accurate, more concise. What is this? E. Plot the results. You couldn't. It's difficult to plot on a Word document, but if you were to plot it, this is what you would see. And this curve is, in fact, an inversely proportional relationship. As the mass increases, the acceleration increases in inverse proportion. Well, so in other words, it decreases. You could have said, as the mass increases, the acceleration decreases. Are you asleep yet? If you are, wake yourself up. Take a pause. Review question 1. If you're still good, carry on. This is question 2. Here's an anonymous man in a wheelchair, and it's a very straightforward thing. Calculate the distance. This is a foundation level sort of question here where they give you the equation, put the numbers in, 10.8 meters for the distance. What would be the reason for the speed of the wheelchair decreasing? Decreasing? What? What could be the reason for the speed of the wheelchair decreasing? I first read that as increasing. No, Mr. Homer, that is wrong. So I should have ticked it started going uphill. Yeah, are you all saying this is where, like in class, everyone goes, no, you're wrong, aren't you? I guess that's probably uphill. Have I got the marked scheme here in front of me on the computer? Yeah, probably. All right. Everyone start to chat. This is where you notice I haven't got any video editing software, so it's all one take. So just hang on in there. If you might find this is it started going uphill. That is correct. Good. What a live bit of error there. Fantastic. Right. So it would slow down, wouldn't it? Fastest, this bit here, steepest gradient, boom, that's your answer. Data logger, I reckon it would give continuous readings, but more frequent readings is a safer bet because I suppose it's not entirely continuous, but it's very frequent. And a data logger gives you more accurate readings, avoiding human error or reaction time error due to the stop clock whole business, and using a tape measure you've got uncertainty in the measurement of distance, so more accurate readings. Great. This graph here, the velocity of the wheelchair changes as it accelerates to a top speed. This is the top speed there, about there, right? Look, yep, that's your top speed. This is constant velocity, zero acceleration. This is constant acceleration to a point to about there, isn't it? Where the acceleration starts to drop away. The velocity still increases, but less so proportionally per unit time, and then eventually we get this constant velocity. Acceleration is zero. Which force reduces the acceleration? Some of you put weight. That's not the case because we're going along flat ground. There'll be air resistance. It's flat ground, look. Boom. So the force that reduces the acceleration, as the velocity increases, air resistance increases until it is equal and opposite to the motor force. And then there is zero resultant force, zero acceleration. And I've explained it here, look. Forces are balanced. Fine. Onwards. The wheelchair starts from rest. it accelerates at a constant rate until it has a speed of 1.5 meters per second. The wheelchair travels at a distance of for a distance of 2 meters while it is accelerating. Calculate the acceleration. Now you'll notice that we haven't been given a time figure here. So the acceleration equation, an equation to do with acceleration that doesn't involve time, is this one on our data sheet. V squared minus u squared equals 2as. S is distance here, or specifically displacement. So this is the one to use, and we know it's the one to use because time has not been specified in the question. Got it? So here we go. I like to rearrange beforehand for things. So for acceleration actually is what we need. So we go A equals, we just divide our v squared minus u squared by 2 and by s to get A by itself. Just take these two underneath and there we go. Put the numbers in. Don't forget to square. Some of you forgot to square your 1.5. 1.5 squared minus 0 because it starts from rest. So that's our initial velocity, 0. Final velocity, 1.5. I know it says speed, but it's all in the same direction, all in one direction. So speed and velocity, same thing in this instance. 2 times our 2 meters. I put 4 in there by mistake, but I'm just writing it out correctly. Boom. 0.5625. How many significant figures should we give this to? We should give it to 2 because there is 2 in the question. So we give it 0.56 meters per second squared. This is why they give you sometimes they give you an answer, a gap for the answer. Put your keep lots of sig figs in your working out up here, and then show the examiner that you've reduced it to 2 sig figs for your final answer. Question 3. Now listen, if you're fading, go and take a break. I'm not, so I'll continue. So Hooke's law, hangs and masses. How's it changed? There's a couple of questions that ask you similar things here. I'm sorry, but so we'll just go through them anyway. Well, the spring, you have 2 ways that the appearance of the spring has changed. It is longer. I've put a bigger distance between turns on the spring. The mark scheme uses the word coils. A spring is coiled, so you could, I think coils is nice too, but turns means the same thing. 2 words for the same thing. The extension of the spring is the distance between which 2 points. The extension is the extra length that the spring has got to over its original unstretched length. So it's from B to C, isn't it? Everyone knows this, and you all got that, I think. Write the equation that links field strength, mass, and weight. You are allowed to put W equals mg because the terms are written here in the question. Be safe and write it out. Weight equals mass times gravitational field strength. What value did the limit of proportionality become exceeded? Well, the best thing to do, a good thing to do on the exam when you're writing it for real, not on a Word document, is get a ruler, draw a straight line along this initially straight line, and where the line departs from the straight line, starts to curve, is where the limit of proportionality starts to become exceeded. And I mean, if you were pedantic, like me, you'd say 4.5 newtons. Look, it just begins to depart, but let's be safe and say 5. And in the examiner's report, you'd be able to say between 5 and 6, I reckon. I put 5. The reason? After this, I like my wording here, everyone, so I'm going to read it. After this force, the relationship is no longer proportional. After this force, the relationship is no longer proportional. Did you say the line starts to curve? You get the mark. That's good. How should the student suggest how the student could obtain a more accurate answer for the limit of proportionality of the spring. You should indicate the additional readings the student should take. So basically what we have to do is take further readings at smaller intervals or reduced intervals between 5 and 6 newtons. In this area here, we want to investigate that area so that we can see more closely where the elbow of the graph occurs, where it starts to bend more accurately. This is just a fill-in line, isn't it? We don't have any data here. We want it. That's what you'd want to get. F equals KE. Oh, see what I did there? Put the numbers in. Now, everyone, several amongst us did not convert. We've got newtons per meter here, not newtons per centimetre. So we have to convert our distance to meters, don't we? I always tell you the safest thing is to use our powers of 10 on the calculator. I know centimetres is times 10 to the minus 2 metres, so I just write it as that. Type it into my calculator like that, and I get 1.152 newtons. 2 sig figs, look, 2 there, so put 2 in the answer. The 5 rounds the 1 up to 2, 1.2. Of course, this is the way to do this if you want to convert it in the old school way. 6.4 divided by 100. There are 100 centimetres in a metre. So the unit size goes up, so your number size goes down. That's a rule, that's always the case. 0.064 metres. You type it in by going 18 times 6.4 times 10 to the minus 2 equals 1.152. Okay, so use your times 10 to the, use the minus sign up here, not the calculation minus sign. This is the text minus sign, it's nicer. And this is how you do it. We'll have millimetres in a minute, which is times 10 to the minus 3. We've got that to look forward to, everyone. So, don't go. Question 4. The extension is between B and C. It's elastic potential energy that's stored in there when it stretches, stretch F. The departure point here is P, again, my straight line. What mistake has the student made here? Look, this should be starting from 0, shouldn't it? They've included the original length in all of their measurements. And we can tell that because the extension would otherwise be 0 were there no force on the spring, but it is not. There is some extension. So I've written the extension is not equal to 0 when F equals 0. I get the marks. Good for me. Part two of question 4. Yeah, we covered that. C. Here we go. Some of us again got 1,800 newtons if you didn't convert to meters for this extension. If you see millimeters or centimeters or kilometers, you think I've got to convert to meters. What is it? Again, I'm just going to show this to you again so we all get into the habit of doing this. Come on, do this. 25 multiplied by 72 millimeters. 72 millimeters. There they go, times 10 to the minus 3. Boom, 1.8. That's our answer. We get all the marks instead of losing a mark for not converting. Still with me? Last question, but it's a long one. So, have a drink of water or something. And here we are. How's the spring changed? Yep, same thing. It got longer. This time I put bigger gaps between coils, just for variety. No other masses were provided. Explain how the student could test if the spring was behaving elastically. Aha, right. So, do we know that? Do we remember this? How do we know? If a spring stays within its elastic limit, you give it back to me after the experiment unstretched, right? It goes back to its original length. Some of you put remove the mass, but didn't put if the spring returns to its original length, it is behaving elastically, or it hasn't gone beyond its elastic limit into its plastic range, where you would have permanent deformation or permanent extension of the spring. B, what's this? Oh, add the missing value. Yep. So we can see the proportional increase here, can't we? Look, it goes up 4 centimeters per Newton. So we would put 8.0 here. You'll got this number. Some of us had it's harder to explain it. So the force is directly proportional to the extension until 4 newtons, right? Because there's a 6 newtons on the number scale here. It goes 4, 4, plus 4, plus 4, plus 4, plus 4, plus 6. What's that? Plus 9. So clearly there's some plastic. We're in the plastic range here, aren't we? So beyond 4 newtons. So I've said, what have I said? Force is directly proportional to extension until 4 newtons. So 4 centimeters per Newton. 2 times 4 is 8 centimeters. That's why I wrote 8. Suggest a value of the force which should happen 4. Yeah. Why? Because extension increases at more than 4 centimeters per Newton after that point. C. Third investigation. 100 gram masses. How's it stored? Elastic potential energy, same as before. Here are our results. Let's have a look at the question and come back to the results table. The value of time for the 100 gram mass in test 2 is anomalous. But value of time, where is it? Test 2. 100 gram mass. This one is anomalous. Yes, it is. Look, it's way higher than the other two. All the rest of these results give 3 close readings. This is what, about 20% higher? Just under 20% higher than these two, which are very close. It's given a mean which is too high. This should be discarded first, shouldn't it? Suggest 2 likely causes. The right answers are that you may have misread the stopwatch, which may give a higher value, or timed too many complete oscillations. That would give you a higher value. These would either have no effect. If you pulled the mass down too far, you might think, well, it's got longer to travel, so that would increase the time that it would take to oscillate. But then thinking again, you'd realise that if you pull the mass down too far, you increase the restoring force of the spring. So you'd stretch the spring more, that would lead to a faster acceleration. So in fact, pulling it down too far doesn't make any difference to the period of oscillation. But these two will affect it, but will give a lower reading. Timing half oscillations by mistake would halve your time. Timing too few complete oscillations would reduce your time, but this is a bigger time, so those are not right. Calculate the mean, easy peasy. It's just the mean between these two values. 4.34 and 4.32, which by inspection, the number between them is 4.33, isn't it? Rounded to 2 sig figs is 4.3. A lot of us had an issue with this question. Why is the mean written to 2 sig figs where the timings are to 3? And there's no obvious reason for this, apart from you have to think a bit outside the box and have a think, okay, what's the experiment? We're using a stop clock here. Well, there's error, uncertainty, of about 0.2 of a second. This is an alert reaction time. It takes about 0.2 of a second, which, if we're reading to 100th of a second on the stop clock, well, the uncertainty in our reaction times, 0.2 of a second switching on, 0.2 of a second switching off, 0.4 of a second. It means we don't need to record our mean to 100th of a second. And I've phrased it as the uncertainty in time readings due to reaction time is about 0.2 of a second, making readings to 0.01 seconds meaningless. See? So she thought that 4 sets of results were not enough, and she's right. The minimum is 7, isn't it? 7 sets of results give us a clear pattern in an experiment. What extra equipment will she need? Well, we shouldn't go beyond the range of the original experiment, so we have to choose masses to give finer readings. So let's choose 50 gram masses. There are 100 gram masses, and then if we had 50 gram masses as well, we could go 50, 100, 150, 200, 250, 300, 350, 400 and get 8 readings, and that would be super. That's it. It's the end of my little video to you. Final thoughts would be physics. Physics is fun, and go for a run. I'm doing this couch to 5k thing. I'm closer to the couch than to 5k at the moment, but it's not where you are, it's where you're going. That is important. There, that's my thought for the day. Okay, stay safe. See you soon. Bye.